Alrighty then. Welcome back to lecture. Okay, does anybody have anything they want me to go over and clarify before we jump in? We're going to finish the chapter today, then we have a worksheet to go over, make sure that the reactions are kind of starting to make their way here. Okay? Maybe here.
Can I submit for
Or
lab?
maybe there. Yes.
Can I submit for lab?
Say, yeah.
So on the homework you gave us, one of the readings has like 10 points on it. What does that mean?
Oh, you know, it's probably just a cut and paste job. Don't worry about it.
Oh, okay.
Does it have a 10 in brackets?
No, it's so like on like the HNMR, it
Oh.
has like 10 points. Like
Let me see, do you have it?
I don't have it.
Ten, please.
Yeah, second one.
Yeah, it's a beast. Love it. It's not 10. What is that, bad boy? Look at that.
Wouldn't that be 2 5s?
Yeah.
Oh.
That's a double of pentaplets. Man, cool.
So what does that mean though? It's double the tablets.
Means it's got somewhere, it's got 4 hydrogens that are similar and 1 that is not.
And it can see all 5.
It sees all 5.
Oh, okay, so just, okay.
Yeah. Yes.
This might sound like a really
Yeah.
dumb question.
Great.
But I'm gonna ask it
I know
anyway. You know in the HNMR, there
Uh-huh.
are lines.
Yes.
And sometimes they were 3, sometimes 2.
Yes.
What do they mean?
Did you not have NMR at Boise State?
We probably did, but
Okay.
it's been a hot minute.
It's been, okay. Let's, so real basic NMR. The rule is called N+1. And that's real basic. We're taking it past N+1. This is what, the reason why you might not have had it at Boise State, other schools, and it's nothing against the schools, some schools teach it in the second semester, some teach it the first semester. It actually, if you look in your book, it's actually chapters 13 and 14. So that kind of implies that it should be taught second semester. What Dr. Nogales and I decided years ago, we want spectroscopy integrated throughout the entire year, not just second semester. So that's why he teaches it first semester. I come back in and reinforce it second semester, okay? So what you would have missed just the basics of the N+1 rule. Let's say I take something like propyl alcohol. Well, let's take ethyl alcohol. It's a great one. It's an awesome one in our society. I'm on 3 expert witness cases right now with this molecule in someone's system. Okay, a great molecule, right? When we look at this molecule, these hydrogens here, okay, these hydrogens here are all identical. They cannot be distinguished, okay? So that's why we say there's 3 hydrogens here. That's the integration, right? That's that line that looks like this, okay? That tells me in there are 1, 2, 3 hydrogens. Okay, that's the integration. Since those are all identical, if they saw no other protons, they would be a singlet. That's it. There's nothing to split them. But because this, what we call spin system, looks over at this carbon, it's an adjacent, it's called, you guys probably didn't have this, but it's called a J3. It's 1, 2, 3, so it's 1, 2, 3 bonds away. That's called the J3. We can do J2 and J4, by the way, but for us, we keep it simple here. We complicate it when we get to elucidation. So these hydrogens look at this carbon and they see 2 hydrogens. So when this one peak looks over and sees this carbon, looks at that hydrogen and says, okay, I'm gonna split because of you. Now it would be a doublet if I just had that. But because I have another one over here, it says, oh, I'm gonna split one more time. And so it becomes a triplet.
Okay.
So these see 2 hydrogens, N+1 tells me, N being the number of hydrogens, it should be N, 2, 1, 2, 3, it should be a triplet, and it is. Okay? These hydrogens are what we call chemically and magnetically equivalent, right? So they're gonna integrate at 2. They look over and they say, look, if we saw no one else, and they don't look through oxygen, by the way, ish. We can if we want to, but we typically don't. They look over and they say, oh, wait a minute. If I didn't see those there, I would be a singlet. But I see that one, so I split. I see that one, so I split again. And I see that one, so I split even again. So I should be a 1, 2, 3, 4, I should be a quartet. N plus 1, right? They see 3 hydrogens, N plus 1, 3 plus 1 is 4, so it should be a quartet. So when I draw the spectrum for this thing, the spectrum is going to look like this. Okay? And there'll probably be, this proton will be way downfield that's typically gets lost. So that tells me then my integration is going to be 2, and my integration is going to be 3. Boom, that's what the spectrum for ethyl alcohol would look like.
Okay, and then, so I guess my second dumb question would be, what is the difference in heights?
Don't worry about the heights. So, you know what's really funny? It's actually kind of funny because at Point Loma, we did have, our NMR was not connected to a computer. What this is, it's the area under these peaks. It's the actual area. So when we were doing lab, we would make a copy of our NMR. We would cut this out like that. And then we would cut this out. And we would take all of those and put them in a micro balance and weigh it. And then we would take the methyl group out, and we would know how much the ethyl group weighed. And then we would take the ethyl group out and know how much the methyl group weighed, and we could integrate that way. That's all it is.
Wow.
Nowadays, the computer does it for us, or the software that I use does it for us. But that's what that actually is. Okay. So the area under the peaks is what this light actually is. Yeah, kind of cool. Okay, so that's NMR. That's like NMR 009 or 090 or something. 100 below 100.
Yeah.
And that's real quick.
Yeah.
So what you might want to go on, since you just come to speed, you could read through chapters 13 and 14 on your own. You could get a PragerU or something out there and try to, or a con series or something on NMR. There's tons on NMR out there. Okay?
Yeah.
Good?
Yeah, that makes a lot more sense.
Okay.
Then. Thank you.
Awesome. Okay, so we're gonna finish this chapter. This chapter deals again with oxidation reduction. It's kind of an interesting chapter in that it keeps talking about reduction, and it really is a chapter on oxidation. So what we're going to talk about, we're going to finish it with the oxidation of a couple functional groups. One of the functional groups that we want to begin to look at is what happens when I have an alcohol. Okay. Now go back to first semester. There's 3 types of alcohol. There are primary alcohols. There are secondary alcohols. And there are tertiary alcohols. And so those are your 3 families of alcohols. Now, alcohol being, and this is what's really important to know with an alcohol, and I'll just review this because it would have been Dr. Nagales. When we think of alcohols, we think of this bond right here, this carbon and this hydroxyl group. That's the alcohol, all right? So this is my special carbon. This carbon has 1 carbon connected to it, therefore it's primary. The special carbon here has 2 carbons connected to it, therefore it's secondary. And likewise, this carbon has 3 carbons connected to it, therefore it's tertiary. Okay? So in the oxidation phase of this carbon, what I'm going to be doing is removing the hydrogen. Because if you remember back to our rules, oxidation is more oxygen and or fewer hydrogen. Reduction is the opposite. Less oxygen and or more or less, or less, more, and or less hydrogen, okay? So, or more hydrogen. So notice this. That can be removed. That can be removed. Nothing on here can be removed. Okay? So that's why this is an important distinction to make between a primary, secondary, and a tertiary alcohol. Primary alcohols have 2 oxidation states. One can be removed, the other can be removed. Secondary alcohols only have one oxidation state. They can only remove one hydrogen. And tertiary alcohols have no hydrogen to remove, so they don't undergo oxidation to a certain extent. You can burn them still, and you can fry them with some really oxidizing compounds, but for practical synthesis, they're not oxidizable. So with primary alcohols, the first step of oxidation for a primary alcohol is going to go to the aldehyde. Okay, so primary alcohols oxidize to aldehydes. Aldehydes oxidize to carboxylic acids. All right? Okay? What we will see when we get to reduction, actually in the aldehyde chapter, so I think it's chapter 18, so it's a ways out, we will see that we can reduce, we can go this way with these reactions. We'll see that carboxylic acids reduce to aldehydes, aldehydes reduce to primary alcohols. Okay, that's in future chapters, so I'm not going to, which is funny, I would have put it in this chapter because the chapter's called oxidation reduction, but it seems to be just an oxidation chapter. Okay, so we're talking about oxidation today. We're going to talk about the reagents that undergo this oxidation step. Okay? Secondary alcohols. Secondary alcohols oxidize to ketones. Okay? Ketones don't further oxidize. Can you further oxidize a ketone? Yes, it's called combustion. You can destroy them and you can make water and carbon dioxide out of them, but that's really not practical. And if you want to see that reaction, just light acetone on fire. Acetone's a real fun one. When I was in lab, we used to spray it on each other's legs and try to catch each other on fire. Real smart, you know, like Paloma. You'd be standing there working on it at your bench and your buddy's got a whole, takes his acetone bottle, sprays an entire, all the way down the lab, up your leg, and he's standing there laughing, and lights the match, and it goes all the way across and up your leg. It's really fun. But that's the oxide, I know, Karen, and he's now an MD PhD. So with that, again, we don't further oxidize these unless we just destroy the molecule, okay, for all practical purposes. So down here, this oxidizes to no reaction. Okay, because if you look at that, there's no hydrogen to take off. Okay, so this carbon is really locked from oxidation. All right? Now, what are the reagents that undergo this? I'll tell you this. It is actually quite difficult, shy of one special reaction that we're going to see, to stop at the aldehyde stage. Okay? Because if you think about it, these hydrogens aren't that different, right? But that hydrogen is different than this hydrogen. Okay, an aldehyde hydrogen became an sp2 bonded hydrogen. Over here in the primary alcohol, we're an sp3 bonded hydrogen. Okay, so you do have that distinction, and there are reactions, like we'll see with the Sorn oxidation, you can stop at the aldehyde, which is really nice. Okay, it's a very important reaction, by the way. All right? If I'm an aggressive oxidizing agent, I don't stop here, I just go all the way. So the reaction goes from a primary alcohol all the way to the carboxylic acid. What would those be? Well, those are going to be your real aggressive oxidizing agents, okay? This is going to be something like potassium permanganate, KMNO4. That's a flashcard. Potassium permanganate is a strong oxidizing agent, and because it's strong, it's going to go all the way and take both protons off, okay? This oxidation, you could use potassium permanganate. It's going to stop there. Potassium permanganate won't burn up the ketone. Okay, it's not that strong, like a match, like oxygen and a spark. So you could use potassium permanganate here as well, right? You hit this with potassium permanganate, you're not going to get anything, right? Again, there's no hydrogen to take off. What else could we use? Well, that's one. One of the other classic one that you need to know, a second flashcard. One is potassium permanganate. The second one is chromic acid. Chromic acid is a very strong oxidizing agent, all right? Chromic acid, when you put when you put chromium trioxide or chromium 6 oxide in with sulfuric acid or even acetic acid, it makes this H2CrO4, makes this chromic acid thing. And that is a very strong, very aggressive oxidizing agent. Okay? Very, very strong oxidizing agent. So that tells me potassium permanganate, chromic acid, will oxidize a primary alcohol to a carboxylic acid. They will also oxidize an aldehyde to a carboxylic acid. Right? So they're strong enough to remove this hydrogen. They're strong enough to remove this hydrogen. So if I have 2, they take both. If I have 1, they take the 1. Okay? So it's really 3 reactions. Oxidation of a primary alcohol with potassium permanganate to a carboxylic acid. Oxidation of a primary alcohol with chromic acid to a carboxylic acid. Oxidation of an aldehyde with potassium permanganate or chromic acid to a carboxylic acid. Okay? And oxidation of a secondary alcohol with either of those to a ketone. Cool? Yes?
So why couldn't you like further oxidize the carboxylic acid?
You can. You can. And here's what it goes to.
Oh, so what does it do to the rest of the carbon chain?
Burns them up, oxidizes them. Poof. Yep. And this is what's happening. I mean, if you think about it, if you look at something like, this, 2, 4, 6, 8, 10, 12, 14, 16. Okay, there's stearic acid. There's what makes steak so amazing. All right, and what your body's basically doing with this enzymatically, it's actually breaking these up and putting those on acetyl coenzyme A, putting them into the citric acid cycle, and you're generating energy from those. You're actually taking the electrons between those carbons, running those through oxidative phosphorylation to reconvert ATP into ATP. Okay? And that's what you're doing. You're on. And what do you exhale?
Carbon dioxide.
And what does your body produce about 300 milliliters a day of through the Krebs cycle?
Water.
Okay? That's all your body's doing. So it's taking a carboxylic acid, just happens to be a real long one, and combusting it, burning it up under enzymatic conditions. Okay? The cool thing about the body is, and what the chemistry, well, it is the chemistry that's doing. The cool thing about the body is it's doing it at 98.6 degrees. And we can do this. Just give me a match, right? But your body can't really tolerate much over 170. You start to decompose. So it's kind of a brutal system. Okay, we good? Yes.
Would the stronger chromic acid ever oxidize the primary carbon in 2 steps?
It does.
It does?
It does. Well, that reaction, when we do these reactions, we always put this in parentheses. We don't, on the flashcard, I wouldn't even have that in there. I would have primary alcohol, 1 arrow, potassium permanganate goes to carboxylic acid.
Okay, so they both go to carboxylic acid.
Yep, they don't stop. It's real hard. So what does stop? Well, there are a couple mild oxidizing agents. Okay, some of the ones that we see in lab. I think we actually are going to see this one in lab. We might see this on lab next Tuesday. I'm not quite sure which one we're going to use. Let's see where my heart there. Okay. So one of them is pyridinium chlorochromate. All right. So pyridinium chlorochromate looks like this. It has a chlorine floating around down here too. Okay, so we don't have to draw this on the flashcard. This is pyridine. All right, we'll get into that when we get into the aromatic chapter. So as a salt, pyridine becomes pyridinium chlorochromate. Okay, we call this pyridinium chlorochromate, PCC. So the flashcard just needs PCC on it. All right, PCC, and there's also PDC. Pyridinium dichromate, has 2 of those, no chlorine. Both of those are considered mild reducing agents. Okay, mild reducing agents. So if I do take a primary alcohol, and I hit it with PDC or PCC, it's going to go to the aldehyde. Okay? They're not strong enough to take off that sp2 proton, so they're considered mild reducing agents. Okay? Good? Now, a couple flashcards we've made here. Oh, and by the way, yes, it would be true that if I had a secondary alcohol under those same conditions, it goes to the ketone, okay? So really, these are all oxidizing steps. They're all oxidizing steps. So, potassium permanganate, chromic acid, PCC, and PDC, okay? But really, the coup de grace of oxidation of primary alcohols to aldehydes, a real, very powerful oxidizing reagent is this oxalate chloride. So let's go through this mechanism. I love to show you mechanisms, because mechanisms are a massive part of what's going on here. How is it that the oxygen's on one of these? How is it that the oxygen here on the chromic acid part of this pulls that off? What's going on? What's the chemistry? So we'll see this. This is called the Swern oxidation. It's a historic, it's a classic. Swern oxidation. So if you put oxalate chloride in with DMSO, this is DMSO, dimethyl sulfoxide. You would have seen dimethyl sulfoxide when you were talking about your competition between your substitution and your elimination. You had a polar aprotic solvent category, if you remember back. We had three solvents. We had nonpolar, polar protic, polar aprotic. Okay, and this is a polar aprotic, it's one of your better ones. This and DMF are your two hot ones. When you put, oops, I'm so sorry, this is a chlorine, not a hydrogen. That's oxalate. These are chlorines, sorry about that. Hence the word oxalate chloride. Okay. When you put the acid chlorides, and we haven't talked about acid chlorides yet, they're really, really aggressive, really corrosive molecules. In fact, yeah, one of my thankfully few tragic moments in lab dealt with an acid chloride. I forgot that I had put a base in my waste container the day before, and I dumped a bunch of acid. That's really, they're really reactive. It exploded on me. It was awesome. They're really aggressive compounds. In the presence of oxalate chloride, this pair of electrons on sulfur goes up. Okay? And so what happens, and this is, you kind of think of this as a resonance structure, but really what happens with this is it goes to this thing here. Okay? And that puts a positive charge on the sulfur. All right? At this stage of the game, what happens is these electrons now see the carbon, that and basically kick off a chlorine. Okay? We will get into the actual, this is a really, there's more to it than this. I'm giving you an abbreviated form. It gets into what we call the tetrahedral intermediate. When we start talking about the carbonyl, I'll go deeper into that, but for now, I'm going to shorthand it with that. That forms this complex, and you can kind of see how this begins to build. It's kind of cool how that works. Plus, we have chlorine buzzing around out here. Okay. Now, when chlorine sees that electrophile, it behaves as a nucleophile attacking the sulfur. What that does is that causes those electrons to come down there, those electrons to go up there, those electrons to go back onto chlorine. So follow the flow here. Again, electrons always go. Electrons are nucleophiles. They're going to go attack an electrophile. So I am nucleophilic up here. I am electrophilic. So I attack. I am nucleophilic. I am electrophilic. So all we're doing is little magnets attracted to little magnets. Okay? Magnet here attracts to magnet here. Those electrons go, and we break this molecule up. What do we break this molecule up to? Well, we break this molecule up to the actual active ingredient that we're going to be working with. So we just completely shredded that molecule apart. We took our oxalo chloride and we basically made this here. And this is our hot molecule, right? Okay. That is our hot molecule. So when I put that in with my alcohol, okay, notice we still have a base acid reaction. The alcohol electrons go to the sulfur. Chloride says, oh, cool, I'll grab that proton and give you your electrons back, oxygen. And at this stage of the game, notice the compound that we get out. Okay, there you go. And it still has a positive charge on it. And we have HCl as a byproduct. Okay? And you still do have chlorine floating around out here. This chlorine right here, this guy right here, he's still floating around, bonding to this. You can kind of think of him floating around up there with that sulfur, if you will. Okay? Now, at this stage of the game, you have a stable compound. Okay? This compound is stable. You can actually isolate this, put it in a jar, good to go. So this is step one. All right, so step one on your flashcard is the addition of oxyl chloride and DMSO to the alcohol, to the primary alcohol. Okay? Step two. What does step two look like? Step two then does this. I have a new reagent. My new reagent is triethylamine. Okay? Triethylamine, T. And a lot of times in a reaction you'll see T underneath one of the arrows. Okay? That's triethylamine. Triethylamine now says, oh, there is a pretty acidic proton right here because of the sulfur doing some hyperconjugation stuff, pulling back on that. So this proton gets taken off, those electrons get put onto carbon. And now you're ready to complete the reaction, and you can see what's going to happen here if we do a really cool rearrangement step. Okay? At this state, notice what happens. Electrons go, attacking the proton on the alcohol. These electrons go here. These electrons go here. So look what your overall reaction gives you. Your overall reaction gives you out as a byproduct neutral. It's now neutralized. Sulfur's happy with just two bonds. But more importantly, what you get out is aldehyde. Okay, so the Swern oxidation is taking a primary, it's a mild way of taking a primary alcohol or secondary alcohol and oxidizing it to the aldehyde. So what would your actual flashcard look like? This is the mechanism on how we got there. What's the practical side of what it would actually look like in my synthetic toolkit? Well, what it would look like is this here. Okay, so what it would actually look like is alcohol, okay, one, and you could even do this C2O2 Cl2 if you want. I mean, or you could draw it. It doesn't matter. But that's basically what it is. DMSO. We typically do this in dichloromethane at minus 78 degrees centigrade. It's a really cold reaction. Okay, we do this at dry ice conditions. Not dry ice, liquid nitrogen. Okay, that's step one. Step two then is to just hit it with triethylamine. And in doing so, the Swern oxidation specifically would give you the aldehyde. Okay, so that's what your flashcard would look like. And I would probably somewhere say this is the Swern oxidation. Because named reactions in organic chemistry are very special. There's a reason why they're named, and when we get into carbon-carbon bond formation, you're gonna see there's a lot of named reactions that we use. Okay, any questions on that? Yes?
I just have one, why did the nitrogen go onto the carbon on the right?
Nitrogen go onto the carbon. Yeah. Why does it attack here instead of here? Yeah. Isn't that ultimately what we're doing? Aren't we trying to get that hydrogen off? The reason for it is this sulfur is withdrawing, it's actually weakening this system. So this is the more acidic, it has a lower pKa than this hydrogen. So when you put the base, it's going to hunt this molecule, it's going to find the proton with the lowest pKa. That has a lower pKa than that, therefore it takes that one off, not that one. But once I form this is called an ylid. This is really a powerful electron. This now is strong enough to take the next acidic proton, it's that one. Yeah, kind of cool, right? Okay? You good? So that's Swern oxidation. Okay? There's another oxidation that's a very specific oxidation, and it's an oxidation. We're not into benzene yet. We will. So it's a hard one to kind of teach at this point because we don't know why this aromatic ring is so special. But basically, if I put this in with manganese 4, okay, manganese 4 is a very special oxidizing. It's very mild. It can only oxidize allylic or benzylic alcohols. Okay? Now, you have had allylic. You've had that probably, I might need to remind you what that word means. But you've had that. We have not had benzylic yet. This is benzene. This carbon right here is a benzylic carbon. I'll get to that. What you have had is allylic. If you remember back when you had an alkene that looked like this position is called allylic. Remember that? The hydrogens here are real special. The carbon there is real special. In fact, that's why if you hit that with NBS, N-bromosuccinimide, it specifically puts a bromine on the allylic position. That was a reaction that you probably saw at some point. Okay? So again, NBS, and if not, we'll see it next chapter again in the free radical section. All right? Special. Allylic and benzylic are special locations, and I'll explain why benzylic is special when we get to the aromatic chapter. So a very mild oxidizing agent with a very reactive set of protons here. Those are really, really reactive protons, allylic and benzylic. It will specifically oxidize only benzylic or allylic. In fact, if I were to throw this molecule in with manganese 4 oxide, look what you get. If I put this molecule in with manganese oxide, you get this. And it's actually nice to have that in your toolbox because it won't touch regular alcohols. All right? They're inert. It won't react with them. It's not strong enough to pull off. It's not strong enough to oxidize this carbon. Okay? It's only strong enough to oxidize a benzylic or allylic protons. All right? So that's a nice reaction to manganese oxide, manganese 4 oxide. All right? Good? We're almost there. Almost landed the plane. Our last two reactions are really kind of fun. Again, they come back to the world of benzene, and we will get into benzene chemistry. But we're going to add two reactions that are actually pretty cool. And there'll be a place for this to really go at it when we get into aromatic chemistry because it's super fun. Okay, so our last two reactions before we work on our worksheet. So if I have nitrobenzene, okay, I have nitrobenzene, and I hit it with tin chloride and HCl, okay, it reduces to aniline. And again, this is the aniline molecule. Okay, so that's aniline. And you see aniline all over the place. In fact, I mean, I'll explain this again when we get into aromatic, but you might not know what this molecule is, but I bet you most of the people in this room have taken this molecule. Okay, you see the nitrogen in there?
Mm-hmm.
This is acetyl aminophenol. Acetaminophenol. Acetaminophen. Okay? So that's Tylenol. All right? So that's a very important molecule, especially in the pandemic with flu. Reducing, it's a true NSAID. Amazing molecule. But we'll talk about molecules like this when we get into aromatic section. So if I go from a nitro, and we will nitrate benzene, this is a really cool reaction. Okay. In fact, if you look at this molecule, just for a little fun, a little trivia, this is one of the most amazing molecules, both socially and financially. Okay. All right. So this molecule here, a methyl group on a benzene ring. This is called the ipsocarbon, which we'll talk about. This is toluene. This is nitrobenzene. So I have three nitros on a toluene. So I have trinitro-toluene. I have trinitro-toluene. That's dynamite. That's TNT. Okay, it's one of those molecules that is, you get a lot of history to that. Okay, so reaction of taking a nitro group, we can hit it with tin chloride and hydrochloric acid, and we can reduce it to the aniline. The other thing that's really cool is I can go the other way with this. I can take an aniline, and I can hit it with dimethyl DMDO. Okay, not DMSO, DMDO. DMDO is dimethyl dioxaran. All right, so dimethyl dioxaran looks like this. This is dimethyl dioxaran. Okay. DMDO, and I won't bore you with the mechanism, it's really trick, puts its two oxygens back on the nitrogen. Isn't that kind of cool? Okay, so that's really nice because now I have a way that I can go, I can either reduce a nitro to an amine, or I can take an amine and oxidize it to the nitro. Okay, so I can go either way, whether I use tin chloride and HCl. And by the way, you can also on this one, I'll put it in brackets, you can also do hydrogen and palladium with this one too. That actually works as well. There's two different ways that you can reduce a nitro to an aniline. Okay? And to complete, I should have these two probably because I'll come back to them, but the last two really in your book are kind of interesting, and I'll use these in synthesis. But if I have the azide and I hit this with hydrogen and palladium, it just goes to the amine. And if I have the nitrile and I hit it with hydrogen and palladium, it also goes to the amine. Okay? So these reactions, the azide goes to the amine. Notice I have 1, 2, 3 carbons, so I have 1, 2, 3 carbons. Here I have 1, 2, 3, 4 carbons. So I should have 1, 2, 3, 4 carbons in my reduced amine. Okay? Questions on any of that? Anything you want me to clarify or go back over? Because that's it for chapter 11. Good? 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 Okay. We have about 13 minutes left. Why don't we just do, let's do a couple of these, see how well. Why don't we do the first 4 and then the first 2 on the next section down. Just see, I would encourage you, these are great questions for practice for the exam. This is what it will look like. So if you're good with these, you're good with the reactions, all right? And so at this point, you're more than welcome to go back through, look at your notes, even pull out your book. So let's have a pretty good overview of what we went through at the end of this chapters. If you want to review that, but I would definitely do that. That should be a key.
Which ones are we doing again?
Do the top 4 and the top 2.
Oh, okay.